Hey friends, welcome to the YouTube channel All About Electronics. In the next couple of videos, we will learn about the different biasing techniques for the JFET. And in this particular video, we will learn about the fixed bias configuration. But before we do that, first of all, let us understand what do we mean by biasing. And to understand that, let us quickly see what we had seen in the last couple of videos. So in the previous videos, we had seen the output and the transfer characteristic of the JFET. And then we had discussed the different regions of operation for the JFET. For example, whenever the JFET is operated in this particular region, then it is known as either ohmic or triode region of operation. And in this region, the JFET works as a variable resistor. So to operate the N-channel JFET in this region, the VDS should be less than VGS minus VP, and of course the value of VGS should be between the 0 and the pinch off voltage. So when this condition is satisfied, then the JFET will operate in this ohmic region. And similarly for the P-channel JFET, the magnitude of VDS should be less than VP minus VGS, because in case of the P-channel JFET, both VP and the VGS are positive. And in this linear region, the drain current ID is a function of both voltage VDS as well as the voltage VGS. And the drain current ID can be given by this expression. And then after, we had seen the saturation or the active region of the JFET. So in this region, the JFET can be used for the linear amplification of the AC signal. And to operate the JFET in this region, the value of voltage VDS should be right hand side of this parabolic curve. Or mathematically, we can say that the value of voltage VDS should be greater than or equal to VGS minus VP. And similarly for the P-channel JFET, the magnitude of the voltage VDS should be greater than or equal to VP minus VGS. So once this condition is satisfied, then the JFET will operate in the saturation region. And in this saturation region, the drain current ID can be given by this expression. So then after we had seen the cutoff region of operation. So in this region of operation, the drain current ID is almost 0. So to operate the JFET in this region, for the N-channel JFET, the value of voltage VGS should be less than or equal to VP. Or in other words, we can say that whenever the voltage VGS is more negative than this pinch off voltage, then the JFET will operate in this cutoff region. And similarly for the P-channel JFET, this voltage VGS should be more than this pinch off voltage VP. So once this condition is satisfied, then the JFET will operate in the cutoff region. And by operating the JFET in the saturation and the cutoff region, it can be used as a switch. So whenever the JFET is operating in the saturation region, then it will act as a closed switch, and whenever it is operating in the cutoff region, then it will act as a open switch. So in this way, by operating the JFET in the different regions, it can be used for the various applications. But to operate the JFET for the various applications, the operating point of the JFET should be selected properly. And here the operating point defines the value of drain current ID and the voltage VDS. So the biasing is the process of selecting the operating voltage and the current of JFET such that it should operate in the specific region. And doing so, it can be used for the specific application. And there are three different biasing techniques which are used for the JFET, which are fixed bias, self bias and the voltage divider bias. And in this particular video, we will learn about the fixed bias configuration. So the circuit diagram which is shown in the figure is the fixed bias configuration of the JFET, which is used for the amplification of the AC signal. So as you can see over here, small input AC signal is applied through this input coupling capacitor Ci, and the output is measured between this drain and the source terminal via this coupling capacitor Cout. And here the biasing voltage and the current for the circuit is set using these two resistors and the voltage sources. Now here we are only interested about the DC operating point of the given circuit, or in other words we can say that we are interested in the DC analysis of the circuit. So for the DC analysis we can consider all the AC sources as 0 and we can consider all the coupling capacitors as a open circuit. So for the DC analysis of the circuit, the equivalent circuit will look like this. Now for the JFET, the input impedance of this gate terminal is very high, or we can say that this gate current Ig is approximately equal to 0. So if that is the case, then there will not be any flow of current through this gate terminal, and due to that we can say that there will not be any voltage drop across this resistor Rg. So in the equivalent circuit, this resistor Rg will act as a short circuit, and considering this point, the equivalent circuit will look like this. So for the given circuit, now we are interested in finding the drain current ID and the voltage between this drain and the source terminal. So let us see how we can find this drain current ID and the voltage between this drain and the source terminal. But before that, first of all let us find out the voltage between this gate and the source terminal. Now if you observe over here, the source terminal is already grounded. So if we apply the KVL for this loop, then we can write it as VGS is equal to minus VGG. So this voltage is appearing between the gate and the source terminal. And from this voltage, we can find the drain current. So we had seen that the drain current ID can be given as IDSS times 1 minus VGS divided by VP whole square. But this expression is valid whenever the JFET is operated in the saturation region. So here let us assume that the JFET is used as an amplifier and it is already operated in the saturation region. So considering this, we can use this expression, and from this expression we can find the value of the current ID. And once we know the value of this drain current ID, then we can easily find the voltage VDS by applying the KVL in this outer loop. So let's apply the KVL in the outer loop and let us find out the expression for this voltage VDS. So for the given circuit, let's say due to this drain current ID, the voltage drop across this resistor RD is equal to VRD. And the voltage drop between this drain and the source terminal is equal to VDS. So applying the KVL in the outer loop, we can write VDD minus VRD minus VDS is equal to 0. Or we can say that this voltage VDS is equal to VDD minus VRD. And here VRD can be written as ID times RD. So this is the expression of the voltage VDS in terms of the drain current ID. So in this way, we can find the drain current ID and the voltage VDS for the given JFET, or in other words, we can find the operating point of the given JFET. So now let us take few examples based on this so that this point will get clear to you. So in this example, we have been given this N-channel JFET and it is configured in the fixed bias configuration. And in this configuration, we have been asked to find the value of voltage VGS, current ID and the voltage VDS. So first of all, let us find out this voltage VDS. Now, like I said earlier, for the JFET, the input impedance is very high, or we can say that this gate current Ig is approximately equal to 0. So considering this, there will not be any voltage drop across this 1 megohm resistor. Or simply in the equivalent circuit, we can consider this 1 megohm resistor as a short circuit. So considering this point, we can say that the voltage VGS will be equal to minus VGG. And here this voltage VGG is equal to 2 volt. So we can say that the voltage VGS will be equal to minus 2 volt. And once we know the value of this voltage VGS, then we can find this drain current ID by using this expression, that is ID is equal to IDSS times 1 minus VGS divided by VP whole square, provided the given circuit is operating in the saturation region. So here, initially let us assume that the JFET is operating in the saturation region. And considering this, let us find out the voltage VDS. And later on, we will validate it by checking the condition VDS is greater than or equal to VGS minus VP. So if this condition will satisfy, then we can say that the JFET is operating in the saturation region. So first of all, let us put the value of VGS in this expression. Now here, we have already given the value of VP and the IDSS. So from this we can say that the drain current ID is equal to 12 times 1 minus 2 divided by minus 6 whole square, or we can say that the drain current ID is equal to 12 times 1 minus 1 by 3 whole square. And if we simplify it, then the drain current ID will be equal to 16 by 3 milliampere. So this drain current ID will flow through this JFET. And once we know the value of this drain current ID, then we can easily find the voltage VDS. So as we have seen, this voltage VDS can be given as VDD minus ID times RD. And here the value of VDD is equal to 15 volt and the current ID which we have found is equal to 16 by 3 milliampere. And the value of this resistor RD is equal to 1.5 kilo ohm, or in other words we can say that it is equal to 3 by 2 kilo ohm. So if we simplify this expression, then the value of voltage VDS will come around as 7 volt. So here the value of voltage VDS is equal to 7 volt and the current ID for the given circuit is equal to 16 by 3 milliampere. Now from this, let us take the condition for the saturation, that is VDS should be greater than or equal to VGS minus VP. So once this condition will get satisfied, then we can say that the JFET is operating in the saturation region. Now here the value of VGS is equal to minus 2 volt and the value of VP is equal to minus 6 volt. That means the VGS minus VP is equal to 4 volt. And here, as the voltage VDS is greater than VGS minus VP, so we can say that indeed the JFET is operating in the saturation region. And due to that, we can use this expression for finding the value of this drain current. So in this way, whenever the JFET is used as an amplifier, then using this method, we can find the value of drain current ID and the voltage VDS for this fixed bias configuration. Now in this example, the values of the resistors as well as the biasing voltages were selected such that the JFET was operating in the saturation region. But let's say if you are designing the circuit by yourself, then you need to select the values of resistors as well as the biasing voltages such that the JFET is indeed operating in the saturation region. So based on that, let us take our second example. So in this example, we have been asked to find the value of this voltage VGG and the value of the resistor RD such that the voltage VDS is equal to 9 volt and the drain current ID for the given circuit is equal to 8 milliampere. Now if you notice over here, the voltage VDS for the given circuit is equal to 9 volt and it is greater than the pinch off voltage VP. So even if we assume the value of VGG as 0 volt, in that condition also the circuit is operating in the saturation region because this voltage VDS is already greater than this voltage VP. That means whenever this voltage VDS is equal to 9 volt, then this JFET will work in the saturation region. So for this circuit, let us find out the value of voltage VGG and the resistor RD. And first of all, we will find the value of this resistor RD such that the voltage across this drain and the source terminal is equal to 9 volt. Now we know that the voltage VDS for the fixed bias configuration can be given as VDD minus ID times RD. Now here the required value of this voltage VDS is equal to 9 volt while the value of VDD is equal to 15 volt. And here the required value of drain current ID is equal to 8 milliampere. And we need to find the value of RD such that these conditions will get fulfilled. So if we rearrange these terms, then we can say that the value of resistor RD should be equal to 6 volt divided by 8 milliampere, that is equal to 750 ohm. So by selecting the value of RD as 750 ohm, we can ensure that the voltage between this drain and the source terminal is equal to 9 volt. So similarly, now let us find out the voltage VGG such that the drain current ID in the given circuit is equal to 8 milliampere. Now as I said earlier, the given circuit is operating in the saturation region, and for that case we can say that the drain current ID is equal to IDSS times 1 minus VGS divided by VP whole square. And from this we can find the value of voltage VGS for the fixed value of drain current ID. So if we rearrange this expression, then in terms of the VGS we can say that voltage VGS is equal to VP times 1 minus under root ID divided by IDSS. Now here the value of voltage VP is equal to minus 6 volt, while the value of current ID is equal to 8 milliampere, and the IDSS for the given circuit is equal to 12 milliampere. So if we solve this expression, then the value of voltage VGS will come around as minus 1.1 volt. Now we know that the voltage VGS is equal to minus VGG. So we can say that the voltage VGG for the given circuit should be equal to 1.1 volt. So in this way, by selecting this voltage VGG as 1.1 volt and the resistor RD as 750 ohm, we can ensure that the voltage VDS in the circuit is equal to 9 volt and the current ID is equal to 8 milliampere. Now so far in our discussion, we have only talked about the N-channel JFET, but similarly the P-channel JFET can be also configured in the fixed bias configuration. So now let us take the third example based on the P-channel JFET. So in this example, the P-channel JFET is configured in the fixed bias configuration, and we have been asked to find the value of voltage VGS, current ID and the voltage VDS. Now first of all, if you observe this circuit looks quite similar to the N-channel JFET circuit, but here now the polarity of the biasing voltage has been reversed. So if you observe, the voltage VDD is negative and the voltage VGG is positive. And for the P-channel JFET, the pinch off voltage VP is also positive. And apart from that, here the drain current will flow from the source terminals towards the drain terminal, because here the source terminal is more positive respect to the drain terminal. So for the given circuit, now let us find out the voltage VGS, current ID and the value of voltage VDS. Now for the given P-channel JFET, as the input impedance is very high, so we can consider this gate current IG as approximately 0 ampere. And if that is the case, then there will not be any voltage drop across this 1 big ohm resistor. And due to that, we can say that this voltage VGS for the given circuit is equal to VGG, because over here if you apply the KVL around this loop, then we can say that the voltage VGG is equal to VGS, and for the given circuit the value of VGG is equal to 2 volt. That means the voltage VGS will be equal to 2 volt. Now once we know the value of voltage VGS, then we can easily find the drain current ID, and we can find it by using this expression, that is ID is equal to IDSS times 1 minus VGS divided by VP whole square, provided the circuit is operating in the saturation region. So once again we will assume that the circuit is operating in the saturation region, and then after we will validate it. So here we have been already given the value of IDSS as well as the pinch off voltage. So let us put the value of VGS in this expression and let us find out the value of the drain current. So the drain current ID will be equal to 10 times 1 minus 2 divided by 4 whole square, that is equal to 10 times 1 by 2 whole square. That means the drain current ID will be equal to 2.1 2.5 milliampere. And once we know the value of this drain current ID, then we can easily find the voltage VDS. So for the given circuit, as the drain current ID is flowing from source to the drain terminal, so we will write the expression of KVL from the source terminals towards the drain terminal. So we can say that the voltage minus VSD minus voltage VRD, that is the voltage across this 2 kilo ohm resistor, minus of minus 12 is equal to 0. That means this voltage minus VSD is equal to minus 12 plus VRD, that is equal to minus 12 plus ID times RD. Now here this voltage minus VSD is nothing but VDS, because if you know, the voltage VSD can be written as voltage Vs minus VD. So minus VSD will be equal to VD minus Vs, or simply it is equal to VDS. And from this we can say that the voltage VDS is equal to minus 12 plus ID times RD, that is equal to minus 12 plus 2.5 milliampere times 2 kilo ohm, that is equal to minus 7 volt. So in this way, for the given circuit, the value of voltage VDS is equal to minus 7 volt and the current ID is equal to 2.5 milliampere. Now let us validate that the given circuit is indeed operating in the saturation region. So for that, the value of the voltage VDS should be greater than or equal to the voltage VP minus VGS. Now here the pinch off voltage VP is equal to 4 volt and for the given circuit VGS is equal to 2 volt. That means this VP minus VGS will be equal to 2 volt, and for the given circuit the magnitude of the voltage VDS is equal to 7 volt. So as this voltage VDS is greater than or equal to the VP minus VGS, so indeed this given circuit is operating in the saturation region, and due to that we can use this expression for the drain current, and using that we can find the value of voltage VDS and the drain current ID. So I hope in this video you understood how the JFET can be configured in the fixed bias configuration. So in the next video we will see that how the JFET can be configured in the self bias configuration. So if you have any question or suggestion, do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.